So before the coffee break, there is Mina Ghodsi. She will be talking about revisiting the angular redshift cosmological test with milliarcsecond product structures in AGN.
It is Mina. I'm a PhD student working under András Kovács and István Csaba, but today I want to talk about another project. I'm not talking about the Ice-Halo effect, something which is kind of related to this morning panel session. Last year I was lucky and I won this grant. This is a Hungarian grant, ECHO. And you can work on another project besides your PhD. So I was lucky I won this, and right now, like for this project, I work under supervision of Sándor Frey, who is also here. So right now I want to talk about the radio astronomy, which is not related to my PhD topic. I think we really wanted to show that we didn't use any veto card for ourselves. So that's why I have the last presentation, the last afternoon, after lunch, but exactly before coffee break. Even right now, I'm thinking about coffee more than my presentation. But if you're very tired and you want to listen to only one slide, this is too long, didn't read the slide. So I try to keep it in a way it confuses you, so make you even more curious to listen. I hope. So we provided and we used the largest single frequency dataset from VLBI. We use a flux-based size model to reduce our dependence on cosmology. We tried to constrain omega n, but we were not successful. We found that there is a degeneracy between omega m and n, and there is a degeneracy between L and n. So I hope this makes you confused that what's L, what's n. And if you're confused, it's good. And if you're not confused, I should say that last slide, I will take a quiz. So still listen to this. But really, there is an exam at the end. So what's the main idea? Why this theta-z, why this test matters? The main idea is very simple. So if we have a class of objects and with a kind of almost a standard linear size, and we can see that in different redshift, different distances from ourselves, we can measure their apparent angular size, and based on and together with the angular diameter distance, we can study the geometry of the universe. And this can be something complementary to, for example, a standard candle, type 1 is supernovae, standard ruler, BAO, or we call this a standard rock. And what's very important here is that we are using radio telescopes, so we can go higher in we can measure, we can see object during high redshift, redshift that maybe, for example, visible traces, they cannot reach to those redshift. So this is something good about this. Okay, I want to talk about happy history in just one slide. So the main idea came from Fred Hoyt in 1959. So he said that if we can use extragalactic radio sources as a standard road. So he said that if we can find object like this, Cygnus A, which is very nice and beautiful, if we can find object like this in different redshifts, we can measure them and we can distinguish between different cosmological models. In 1970, people started to work on this. So they started to use VLA dataset. At that time, it was like arcsecond resolution. And they tried to implement this method and they were not successful. So they said that maybe the radio galaxies, they are not the standard rock. They're not very good. But again, in 19, this came back, but with two different changes. First of all, they used VLBI, which has a higher resolution rather than VLA. And they also use jet structures in AGN instead of previous radio galaxies. And actually, this plot here is from this paper from Leonid Kenkelerman and Sándor Frey. By the way, three of them, they're also co-author of this paper that we submitted a few days ago. And all of these data are fresh from the oven, so less than 1 week ago. Anyway, but I took it from this website. Also added Euclidean, but the main idea, the plot or the figure is coming from this paper. So what they found at that time, this is in 1990, they literally used with a little data set, so 18 data, 50 or something like this. So finally, we reached in 1991. This group, they provide a data set of 330 samples. And they showed that, like, at that time, we can distinguish between cosmological model that they have omega n for a steady state, or even something which is like completely opposite, Euclidean. So you can see this data, there is a kind of turning point in the redshift 1.3, 1.5. So it shows that, like, okay, like this kind of model is better with this data set rather than, for example, a steady state or Euclidean. Okay, in the last few days, I think Sean Sapudi mentioned about the system of trust. So most of the part of our group, they work on the map level, and I prefer to trust them. So I have no idea how they literally extract this data from VLBI, what they have done to extract this table. So I got table from them and I use that. But I can see from Shandor's face that he would be more than happy to explain during coffee break that how they extracted this, but don't ask me about this. So I try to, if you believe in the system of trust, listen to the next few slides. If you have trust issue, I will talk about those things again. So like after that. So let's start from, this is my beloved meme, actually. So this is the data that we have. So we have 4,240 data from redshift 0.1 to 6.5. You can see it's very high redshift, and it's like a only X-band around 8 gigahertz from VLBI and like jetted AGN, etc. So this is the theta versus z that we have. Okay, let's talk about the equation, or the only equation that we have here. It will relate it to exam. So what we have here, we have a relation between theta, the angular size, and redshift. So but in between, we have, for example, L, the linear size scaling factor in parsec. We have flux density. We have a parameter to normalize this flux density. We have a free parameter here related to flux. And we have this, which is kind of explain the size evolution. And more important, we also have the angular diameter distance, which we can implement our cosmology here. What we have from our data set, from that table, if we trust them, we can read the observed angular size and its uncertainty. We can read the flux density and its uncertainty, and we can read redshift. What we like to constrain is these 4 parameters. 3 of them, L, beta, and n, they are coming from astrophysics, and we are also, we want to constrain cosmology. So we also want to constrain omega n. So we want to constrain 4 free parameters. And we have some parameters that we are fixing that. For example, everything here in all of my results, we fix h naught equals to 70 for the speed of light, etc. We also consider something very, very simple. So we want to constrain 4 parameters. Let's start from data. So we have this equation, we have data, we can run MCMC. And what you can see here is that I'm only constraining 3 parameters, L, beta, and n, and omega n is not here. Because what we learned is that we cannot, or like we can constrain omega n. So it wasn't successful. That's why I fixed omega n 0.2, 0.3, 0.4, and 0.5. Okay, so we were not successful to constrain cosmology here. So let's go 1 layer down and check the robustness of our empirical equations. So let's check the, like, what's happening in the equations really through this relation between theta and z. So like, who said that we shouldn't show table? But sorry, we have, so this is the kind of table. So this is the first 10 rows. This is the kind of data set that I have for more than 4,000. So I have redshift, flux density, its uncertainty, theta, and its uncertainty. What we have done here is that we fix everything else, but we shuffle redshift. So I extract all the redshift column, I shuffled it, and again I put it back. And I repeated this 100 times, and for each of these 100 month catalog, I ran MCMC, I ran my pipeline. And this is the histogram of, for example, those values for L that I could get. And this red line here is that when I use real data. So this cannot be by chance. You can see there are more than 3 sigma deviation. And this is one of the smallest one. For different frequency or for different table as like input we use, we reach even to higher than 8 sigma deviation. So this cannot be like just by random. So if we have, for example, this specific frequency and this specific angular size, that should be kind of redshift. Cannot be just by chance. Okay, for people with trust issue. Let's go another layer down and use mock catalog instead of real data. Okay, so I will try to be fast. So we created our own mock catalog. So I'm not using the real data here. So I'm just considering a cosmology for myself. So H0 equals to 17, for example, omega 0.3, and I consider something for LM, for example, 5 parsec. So from this value, I can read theta. And after that, on top of that, I added 10%, 20%, and 50% noise, Gaussian noise on top of that. So I'm creating mock catalog. And I gave that as input to check and validate our pipeline. Look, this is like one of the last things, but like we can get back all the assumption we use, like this cosmological parameters, everything. If we add flux density, I can add more, it can be a little bit more confusing. We can talk about that later. But the only thing I want to show you here is that there is a degeneracy between these two parameters, L and beta. Two of those 4 free parameters. And again, let's go to the simplest layer. No MCMC, no data. So like put everything aside. So I'm not using my pipeline. I'm not using any real data. Just look at the model itself. So I'm putting all the parameters which are related to redshift in the right-hand side and everything else, for example, in the left-hand side. And if I plot this versus redshift, this part, in the left panel, what you can see here, I'm fixing parameter n, and I'm changing parameter omega n. It's a little bit hard, but still you can see a little bit distinguish between different cosmological models, yes? But just consider that my real data in the very beginning was very scattered, that's like kind of impossible. But still you can see in high redshift, you can see some deviation. But if I, at the same time, change parameter n, it's almost impossible to distinguish different curves here. And I'm not even talking about our data set and how much it's scattered. So there's also degeneracy between these two parameters. So with just one simple equation that I have, with this one simple likelihood that I'm considering, and this kind of data with all its rate scattered, seems that it's not possible to constrain this. So what I want to say is that this jetted AGN measured with VLBI can serve as a standard rods, but cosmology and source evolution remain strongly degenerate unless there would be different point of view. This is, if you want, you can scan this QR code and you can answer to this. So one of the options to solve this problem is that using multi-frequency observation. Actually, to be honest, we have for different bands. So we only provided here X-band, but we already have the other bands. The other thing is that find a way to reduce the scatter. I know that, for example, Shadow won't be happy to remove data or doing the spinning method, but we should find a way to reduce the scatter of our data. The other one is coming up with something more sophisticated for our likelihood. Consider for example, right now we are just considering uncertainty of theta, but maybe we can consider uncertainty of flux density and redshift as Anders likes. And what I've learned so far in the last 2 years from observational cosmology and astrophysics, that we should always say that we need a larger sample. So this is a must. So you should write this that we more sample. And to be honest, in 1991, Shannon wrote this. So at that time, they said that we have 330 with 1,000, for example, I don't know, with more data, we can constrain better. But right now, we are in that future after 25, 26 years. And we show that even with 4,000 data, more than 4,000 data cannot constrain even without using this. So you can scan this, you can answer to this, or you can even add one more thing if you want. And I really check, and if later we can discuss about this. Thank you very much. If you really want to answer to this.
Any questions first, or in the meantime,
take this exam series.
I just wonder if you learned something about jets from this, or jets smaller or bigger in high redshift galaxies compared to low redshift galaxies. Are there predictions? Galaxies are denser, high redshift, maybe jets have trouble getting out.
I think Sanders.
And you saw in the data, it's pretty much scattered, but the data points are kind of constant, roughly. But there is very little change because there's cosmological evolution, and you compare here apples and pears because the luminosities of these sources are different at lower redshift and higher redshift by like 6 orders of magnitude. So it's very difficult to compare them directly.
Very lucky of you.
So in this figure in theta, it looks like somewhat bimodal. Do we have any information of why this slight bimodality, that you have a dense chunk at around 10 to the 0 and a smaller one around 10 to the 1? Yes.
This is the size we measure.
Yeah, it should have been filtered out, but that was a deadline for submitting this.
That's one of the beauty of this scholarship or this grant. So we have to submit by the end of August. Otherwise, I should give back money to the government. So like.
These are not the typical jet sources, but these are kind of double objects. Well, physically not the same.
Yeah, I think what you've demonstrated is you need to be able to predict the evolution. Because if you knew that, everything would be fine.
Yeah.
And there's some hope of this, because in modern galaxy formation models, feedback on star formation from jets is an essential ingredient. So the galaxy formation modelers are actually building models that are doing what you need, and there's going to be constraints on those from all the stellar evolution properties. So once those are consistently modeled, you may well be able to get some predictions that you can believe on how the jets should evolve.
Yeah.
I'm not saying those exist at the moment. There's a way forward.
Actually, that would be one of the ideas. So we can extract a subset of this data set to have n around 0, to keep n around 0. Do you mean this? To say that, oh, okay, these are like a standard rod, real standard rod, because there is no evolution. I have a subset.
Well, I think it's unlikely you could do that. What I'm saying is that you've got an empirical parallel dependency, and that's just an expression of, well, ignorance is a pejorative word, but you're saying, I don't believe I have a theory for what the evolution is. And I'm saying that such a theory will be constructed by the simulators in due course.
0.5, that's like it's way expensive.
Back to the significance figure. So how it is changing if you just cut the whole thing in redshift? This is the same problem as it was mentioned earlier, or back to the other figure which was discussed. But if you have two classes or two regions divided by 0.3 or 0.4 redshift, they can produce a different kind of figure, or it is not depending on the redshift?
For this one?
This one,
We
yes.
have to fix cosmology.
Pardon?
We have to fix cosmology, so we have to fix both H naught and omega n for this. So for example, this one omega is 0.3 and H naught is 7.
But what I'm asking is about if you leave out the 4 lowest redshift points in this data set, what will happen with the significance?
Yeah,
Not here, but here you can see that there is some kind of thing is happening around 0.4 or 0.5. And what is happening if you just keep the high Z part of the data, and not only here, but in your other kind of investigation?
Yeah, that's a good question. Actually, here we also covered this already. So our real data is like 4,500 and it's a subset from 0.01. But like the place that you want to cut this, it can literally bias your data result for L. So if you cut it, for example, from 0.5, which like mentioned in a few papers from early 2000, this can increase the value of L. So for example, instead of 2 point something that we reach, or 3, almost 3, you can reach even to 12 parsec.
Yeah,
So
but
it can,
that is the region where the real data is in the simulation, right?
yes, but here actually the main idea behind this project was that use as much as possible all data. So
Yeah,
otherwise
yeah,
we should come up with
I
a
was just
real
wondering about the other figures.
figures.
The figure with the red line and the probability and so on. That's
This one?
so if you leave out the 4 or 5 lowest achieved data from it, the whole thing will move up in public, right?
Like if I want to, I don't know, cut from 0.5, I should lose 1/3 of all of my data.
Yes, that's right.
It's not just for 2 or 3 data.
Yeah, but
But you can do infinite versions of cuts, so that's.
no.
We did this actually, we
It
went,
was not done, but, yeah,
we have done like, we
I
have
just wondered
cutted,
about what is happening.
L value will increase, so you will bias human.
So it will get reach the.
But at that time, so the red line also will increase. So
So
if I cut everything, so if I like cut my real data at the
into
beginning,
half,
yes, so for example, 0.5, because right now I do remember it, real L, this red line will reach to 12, and all of this again. So I'm not sure about like what exactly this sigma will be, but all of them will shift
That
to
was
the
my-
bigger L.
my
Yes,
interesting-
yes. But the real data also will increase.
yeah.
When we are removing very low L, the value for L will increase, so that will add one more layer of bias.
Okay, more data.
Yes.
Okay, so let's thank Mina again.